All right. Good morning, good evening, good afternoon, whatever time it is when you're watching this video. This is our day 9 lecture. So let me go ahead and share my screen here as we get into the schedule for the class. So this is our day 9 lecture material where we are going to be covering one textbook section. We're going to be looking at textbook section 3.4 today, so maybe a little bit shorter. The last video ran a little bit longer, so this one a little bit shorter, help balance things out. Um, so we're going to be looking at section 3.4 today. We also do not have a participation day question published with this lecture video. I hadn't quite gotten a chance to write up a participation question. So don't worry about one for this lecture video. There won't be one due that goes along with this lecture, so don't worry about that. There are still other homeworks that are coming up. They're going to be due associated with these lecture materials, so you can still do those. But again, no participation question is going to be covered in this video. All right. So let's go ahead and get into our textbook material as we're looking at section 3.4, where we want to highlight some special facts, some rules that we have to keep in mind anytime we're dealing with probability and a union of two different events. So for this, I'm actually going to switch to the whiteboard behind me. So let me turn off my screen share. All right. So what's the concern we really have to worry about here? Well, we previously have talked about how the word or is used when we're talking about trying to calculate a union between multiple events. Hold on, let me move. I got a light set up in here. It's kind of shiny and funny off things. Okay, that's a little bit better. Um, so when we say find the probability of an event or find the probability of another event, we're talking about the union between those two events. However, if we think about a Venn diagram for a moment, I have event A and I have event B here. And I can say, well, what is the probability of A? The probability of A, if both sets, both events are inside of my sample space, then the probability of A, as we've talked about previously, we are looking at all of the sample points in A, so whatever is inside of A, take all those sample points, find the probabilities of each of those points, and then add them all together. That's what A is, right? This is in blue here. But the probability of B, on the other hand, well, the same idea, except it's all the sample points in the event in the set for B, right? But here, okay, you can kind of see the issue, what's happening here, is that when I try to calculate the probability of the union of these two guys, well, as we previously said, the union means that I'm taking both events and I'm dumping them all together, right? We saw examples of this from the last video, where if I have a set A and a set B, I take them, I mix them together, and that is the union between multiple events, all right? However, if I'm trying to calculate the probabilities separately from these two pieces, then unfortunately, it is not simply just found by adding these two probabilities together. What's the issue here? Well, the probability of A, that includes everything I see inside of A. The probability of B, that includes everything we see inside of B. But if the two events have any overlap, then I just double counted that overlap. That's an issue, right? So in general, if I'm trying to find the probability of a union of two events, I can add them together with the caveat that we have to subtract out that double count. I have to subtract probability of their intersection, that space that they share in common, and by subtracting it one time, then I only count that area once instead of double counting it, and thus then giving me the correct answer. This is called the additive rule for probability. I can add the probability of two events together so long as I'm not double counting whatever they share in common. That then will give me the probability of its union. All right. So we have this first example in the textbook. This is example 3.11, which goes along with this example. So I'm going to erase here what I have on the board. You want to write down this property, this rule. We're going to make use of it in just a moment. And we're looking at this exercise for data for a hospital. Again, referencing patients who are admitted into the hospital and what kind of surgeries they've been admitted for. All right, so this is on page 137 of the textbook. This is the first example, example 3.11. All right. Now, in this example, the records show that for this hospital, so we have this example, for a hospital, we have the case that 12% of all patients are admitted for surgical treatment. They're there to get some kind of surgery. So for surgery. All right. We're told that 16% are admitted for obstetrics. So that is 16% of all patients, blah, blah, blah. I'm just doing dot, dot, dot here because it's the same wording. Of all patients are admitted for obstetrics. And then we have 2% who receive both obstetrics and surgery. 2%, blah, 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 who are getting both, right? Now, if I want to ask the question, I look at a random patient who's walking through the door of this hospital. What are the odds that this person is coming in for, they're being admitted for surgery, for obstetrics, or for both? All right. So first I want to define what are the events here? What are my sets that I want to talk about here? So let's let A be the event that this is a person who's here for surgery. And let's let B be the event that someone is here for obstetrics. Okay. Now, some of this information is already given to us in the question. What is the probability that someone is here for surgery? Well, 12% of all patients are here for surgery, right? So the probability of A as a decimal, I would write 12% as 0.12. Okay. By the same argument, then, the probability of B can be written as 0.16. Okay, that's fine. And then if we're talking about both, well, that's also given. But what does both mean in terms of set theoretic operations? If I have a set A, and this is surgery, here's my set B, that's obstetrics. The both, those are people who are in the intersection between the two sets. These are people who are getting surgery and getting obstetrics. They're part of the 12% and they're part of the 16% at the same time. They're in both sets. And so if they're in both at the same time, when we say the word both, or in other words, think like the word and, we saw in the last lecture, that the word and, this is what we use for the intersection. So the probability of both, that's the same thing as the probability of their intersection. And that is also given to us in the question. The probability of both then is 2%. Okay. So we can answer this initial question. Percentage a person is here for surgery. Percentage someone here is for obstetrics. The percentage somebody is here for both. What have we not answered yet? Well, we'd like to know. Maybe a random person comes in. I don't care if they're here for surgery or obstetrics. I just want to know, what are the odds they're here for one or the other? The word or is a different question then. We're talking about a union. All right. So we're going to have to use that additive rule that we just had written down a moment ago. The probability that they are here for surgery or obstetrics, that means we're calculating a union. And at first, I could just try to add them together, right? However, what's the issue, as we've highlighted here? The problem is that, well, some of the people here for surgery, some of this A event, this A set, some of those people are also getting obstetrics at the exact same time or during their same stay at the hospital. But same argument, some people here for obstetrics may also be here to get surgery during their stay. So there's some overlap here that I might be double counting, where their intersection is double counted. So we have to subtract their intersection, or in other words, subtract where they overlap, subtract the both. So my answer here will be 0.12 plus 0.16 minus 0.02 to give us, oops, that's going off the screen. This will give us a final answer of 0.26. So let me put that back on the screen here. There we go. 0.26 for our answer here. Excuse me. Excuse me again. For finding the probability of the word or, we're dealing with the union, and so we have to use this additive rule to get to our final answer. All right. Now we see this textbook does the same thing here, but I wanted to talk through this step by step on the whiteboard, sort of explain the rationale behind why we're doing this. All right. So we have this additive rule. However, there are other cases, other examples of how this rule could be applied. In particular, we know the whole issue with this rule is dependent on, well, what if their intersection is being double counted? Alternatively, what if their intersection is not being double counted? Or in other words, what if their intersection is actually empty? So let's look at something like this, see how this would work out. So previously we've talked about the dice rolling example, right? If I have a six-sided die and I roll the dice, so roll a fair six-sided die. And again, when I say fair, this means we assume that it's equally likely to be any number, equally likely to be any number on the die, right? So we have this, and I could have different events here. Let's say A is the event that I get a 1 or a 2. And let's say that B is the event that we get a 5 or a 6. Well, in terms of drawing our Venn diagrams now, A has 1 and 2 inside of it. B has 5 and 6 inside of it. But my two sets, they don't share anything in common. Their intersection is empty. So now, if I were to try to calculate the probability of their union, well, the probability of A, that gives me everything inside of A, plus the probability of B, that gives me the probability of B. But now, since there is no overlap, they don't share anything in common, right? They're not crossing. There's no number I'm double counting by accident because they share it in common. I don't have to worry about subtracting their intersection. In fact, their intersection is empty. Right? If I look at their intersection, they share nothing in common. Their intersection is an empty set with nothing inside of it. And so if you're trying to look at the probability of an empty set like this, well, there's no sample points in that intersection. The probability of nothing then is just 0. So there's no intersection to subtract off. We don't have to worry about it. The intersection, the probability of it, is 0, so we don't have to subtract it. So this is a variation of that additive rule, which just says that if our events are what is called mutually exclusive, then the probability of their union is just adding the two probabilities together, and that's it. Easy peasy, right? So again, what was that word I was just using? That is the definition for mutually exclusive. Now, they give this definition in the textbook, so I'm going to switch to sharing my screen here. So let me share my screen, going back to the textbook. And we have here this definition. Two events are called mutually exclusive if, let me move that light. They are called mutually exclusive if their intersection contains no sample points. In other words, the intersection is empty. And we have this picture on the side, same picture like what I drew on the board here. When they are mutually exclusive, that means they don't overlap. Their intersection is empty. We don't have to worry about trying to subtract it out because there's nothing there. Nothing is being overlapped or double counted. All right. And so this gives us an updated probability for the union. If they're mutually exclusive, then we don't have to subtract it and we're on our way. Okay? So they then give us this next example. Consider tossing two fair coins, and we're talking about the probability of observing at least one heads. Now we saw last class, got to be careful with the word at least. If I'm tossing the coin twice, that means I could have one heads or I could have two heads, right? Now look at how the events are defined. A is the event that we actually care about. A is the event where I have at least one or heads. That means one or two heads. The or is implied there as I say the word at least. The event A is happy if I have one or two. Just like if you go to the ice cream shop and they say, do you want vanilla or chocolate? If you only say vanilla, that is a valid response to give. If you only say chocolate, that is a valid answer to a question with the word or. But I can break this up into pieces. Event B, these are the outcomes of flipping two coins where I only have exactly one head. Well, we've seen this before. That would be heads, tails, or that would be tails, heads, right? Event C is where I get exactly two heads. There's only one way to do that. That means I got heads, heads after flipping the coin twice. Now, B and C are completely mutually exclusive. They share nothing in common, right? B only has stuff with one head. C only has stuff with two heads. But together, they do represent the event A. And there are times where if you are trying to find the probability of some big set, some big event like A, it may be easier to break it apart into smaller pieces. A is the same thing as B union C, and they're mutually exclusive. So if A is really hard to find, just focus on these smaller pieces. Find B, and then find C, and since they're mutually exclusive, I can just add them together in the end, and that will get me to a final answer. And that's exactly what they do here in the example. The probability of the A is the same thing as their union, B and C, but since they're mutually exclusive, I'm just adding their probabilities together. But B, that was the case of having exactly one heads. Well, there was two ways for that to happen. And for flipping a coin twice, we've seen this example before. There are a total of four outcomes. 2 out of 4. The probability of B is 1/2. For C, where I have exactly heads, heads, and they show this picture to the left, right? A is this big event, but I can break it up into these two smaller events, the event B and the event C. And they don't share any points in common. C has 1 out of 4, I add them together, and now I have my answer for A, which is a total of 3 out of 4. Now, yes, it's true for this example. It's small enough, it's simple enough. You wouldn't really need to break A apart to find this answer. But the point here is that, well, what if A has 10 or 20 or 100 different points? Then it might be easier to break A apart into smaller chunks instead of trying to find all 100 of those points all at the same time. All right. So at times, this rule can make a larger, more complicated question more easy to look at, more easy to deal with. Okay. And this will conclude section 3.4. Again, there is no participation question to go along with this video, so this will be ending a little bit early. But in our next lecture for day 10, we will be covering two textbook sections to wrap up chapter 3 before our break. All right. So we're going to be looking into that in the day 10 video. This is all I wanted to cover for now in this video, a little bit smaller, but take the break, take a breather, work on homework or catch up on old material. And of course, as always, if you have questions, feel free to email me, come by office hours, let me know. Otherwise, best of luck. I will see you in the next video. I hope you all have a good day, good morning, good night, whatever it is, and I will see you next time.